All right, so we're going to, chapter 4, part 1, we're going to get into just the first piece of what we call frame analysis or truss analysis. There's two techniques that we're going to use, and we're going to tackle the other one next week. So we're going to talk about, as an introduction today, what a truss is, a little bit terminology, those kind of things. Then we'll look at truss behavior, and then there's two broad methods out there, what is called method of joints and method of sections for doing your analysis. We're going to be looking strictly at method of joints today, and then I'll follow that up next week with method of sections. Okay, so let's begin taking a look at a truss. And trusses and frames both are really going to be the major thing you see for large structures, and typically you see them all over the place, but things like bridges are all truss type structures. Some roofs, and most roofs probably, your larger roofs particularly, towers, cranes. So you guys get the idea, and they have a particular look to them, as we'll see. But the analysis of these structures is going to consist in breaking them down into smaller free bodies. So free body diagrams are going to be really, really key. And that was the one thing, I didn't see a lot of free body diagrams in that first test. So we're going to need to make sure that we're really understanding these free body diagrams. And when you break things down, you're going to have to make sure you get all of the elements that go with it. So when you do break them down into smaller items, as it's talking about here, smaller free bodies, you're going to be able to determine forces acting within individual elements. So what we've been doing at chapter 3 is primarily looking at one structure, but we're not looking at any of the interior elements within it. So if we had a truss structure in chapter 3, we just looked at the support reactions. So what this method will do, what we'll be looking at, is breaking this down into smaller pieces and attacking each element. So there is a distinction between a truss and a frame. Technically, they're the same in the way they would look, but it has to do with the way the application of forces in the members work. So for a truss, which is what we're going to be looking at, it's considered to be pin connected. And I'll explain that here a little bit further in a minute. But what that means is we're modeling it that way. So it's not the reality. It's just the way we're saying this thing is. So we call it a pin connected. And it ideally has all of its members in either pure axial tension or pure axial compression. So what we're saying there is that the line of action it's coming right through the middle of the member, the center line of the member, and it's putting that member either in pure tension or pure compression. Okay, so in other words, it's either pulling on that member or pushing on that member. And you might recall we talked about a line force in chapter 3. It was the very first type of force we talked about. So these are considered what are called two force members, because you have two going in or two going out kind of thing. So a frame, a little different. It's a pin connected structure also. That's, again, the way we model it. That's not the reality, which has some two force members, but the thing that makes frames a little bit more involved is that they're also subjected to bending. And bending is a much more complicated behavior to deal with, model, and to solve. So the good news is we're not going to deal with this. Frames can be a little tricky if you go in and do some of the connections, but what you're really doing with frames, which will be different here in the trusses, you're going to be actually solving the member forces, action, tension, or compression. In frames, you're kind of solving the pin connection forces. Okay, so it's a little bit different, but the good news is we don't have to deal with frames, just trusses. So here's a good example of a two-force member. And we're looking at the member in the top, and you can see the member in the top is in tension. So the forces are going away, and they have to be equal and opposite. Remember, for equilibrium to occur. So you can't have force left higher than force right, okay? The same thing is with this compression concept. With compression, we have the forces going in, and they follow along a line there. Okay, so there's a line going across that. Okay, so these are what we consider two force members. Also, you can notice the little holes I've shown in there. Those would be your pin connections. Okay, and the reality is that's not really how things are done in the real world, but that's how we're going to model it. All right. So a truss, as we look at its behavior, it's just typically a framework of members that are triangles, and we're going to consider them all lying in the same plane, but that's not really true, because if you have a three-dimensional bridge structure, you really have it, obviously one side of the truss and another side of the truss and the bottom of the truss and the top of the truss. So all of that works together. It's all stitched together. But if you think about it and look at it, you see that it really is just a series of triangles. And the reason that we use triangles is because the triangular arrangement yields a very, very stable shape. So without that, if you just had a typical type of truss, it would really tend to crash if you don't have that. I don't think I've got a picture here. Yeah, let me do something here. Let me come over here a minute and show you kind of what I'm talking about. Oops, that's not what I wanted to do. Well, all right, hold on a sec. So if we have, let's say, this picture here, that's not the one I want to look at, but let me draw another one here. So if that was your truss, okay, and you had it supported, let's put a simple support here, and you have a simple support here, and let's say you're pushing that thing with a force right there. What kind of supports do I have on this, by the way? What's this down here?
It's a pin.
It's a pin, right? And this is what?
Roller.
All right. So there's no problem with the supports. You agree? The supports could sustain this. Everybody agree with that?
Yeah.
Okay, but the problem is that without any kind of middle connection, this thing would tend to just rack. Particularly if you think that this is a pin connection here and a pin connection, right? What would happen is if you pushed on that, what it's going to want to do is kind of rack it this way. Does everybody see what I'm getting at?
Yeah.
Okay, so if we took and make a triangle, what we've done is by putting that bracing in there, you might call that, that triangle right here is helping to sustain all that load. As a matter of fact, you could actually get rid of these two pieces up here and that truss would be completely stable. So the idea being is that trusses are basically just a system of triangles. And what we're going to be doing is analyzing like what's happening at this joint, what's happening at this joint, what's happening at this joint, and thereby we'll be able to get the reactions of these points. Okay, so we'll come back to this here. Let me go back to my PowerPoint, and I'm going to pick up from the current slide. Let me see where I was. Okay, there's our two force members. Okay, so trusses, if you have your book, you know where my book is. Hold on a minute. If you look on page, let's see, 433. You look on page 107. There are many types of trusses that have been developed over time, and they're usually named by the developer or the engineer that developed that truss. So you notice there's what they call Pratt truss, Warren truss. So those are all names of the people that developed them. And these are all widely used configurations. So if you look at certain like bridge structures or cranes or those kind of things, you're liable to see a lot of these types of trusses. So they have a long history of being utilized. They have long stability in what they're doing. Um, and we're not going to look at any particular ones, but you might want to take a check that out. That's on page 107 in that figure 4.3. Okay, so what I like to do, and this is not in your book, I like to talk a little bit about terminology that's typically used with trusses, okay? So I've created a picture for you on the next slide, but we have what's called a support, a span, a panel, and a height. So these are all distance kind of relations. And then you have members that are called lower chords and upper chord members, and then you have web members, okay? So you have your supports, which we're used to from chapter 3. Those are primarily going to be one of two types. You're typically going to see pins and rollers, okay? Distances are going to be related as either spans, panels, or heights. We'll get there in a minute. And then members are lower chord members, upper chord members, or web members. And then the other thing you'll have in trusses is joints. And we're going to be solving joint problems, okay? But actually, by solving joints, we're going to be getting member forces. So this picture here is from another book that I actually used when I was in taking statics, and I think it's a really good picture. This shows you that truss terminology. So notice supports, they're clearly shown. In this case, here's a support on that side, and there's a support on B, or actually that's 8. Okay, so we have support at 1, support at 8, and notice usually you're going to have a pin and a roller. If we put 2 pins on there, it becomes statically indeterminate for us. So we're going to almost always see that in these problems. In fact, I think you always will. So distances, notice span is usually the distance from support to support, but it could also be the distance of the total truss. So if you move that support at 8 over to 7, the truss span would still go from end of truss to end of truss. Okay, so it's the total distance that that truss is spanning. A panel is usually a subdivision of the span, and so notice from 1 to 3, I think that is a span, and then from 3 to 4, I'm sorry, is a panel, and 3 to 4 is a panel, and 4 to 5, 7, and 7 to 8. Those are all typically the same distance, okay? So when I hear, like you might say you have 5 panels at 20 feet, that would tell you you have 5 panels, 1, 2, 3, 4, 5. So that would be important. In this case, you'd have 1, 2, 3, 4 panels. All right, height is a distance from this lower grouping of members to the upper grouping of members. So that's your height, okay? Then we have members themselves. So member 1, 3, 3, 4, 4, 7, and 7, 8. Those members are referred to as the lower chord members. And the upper chord members would be 2, 5, and 5, 6. All right. Anything else is a web member, just kind of like a spider web concept. So if we go 1 to 2, 2 to 3, 2 to 5, 4, those become what are called web members. And as far as the analyzing this truss goes, it really doesn't matter whether you're working at an upper chord or lower chord, because you're just going to solve joints. So that doesn't really come into play too much. Then the other thing are what are called joints, and you can see the joints listed on there. I've got joints 6 and 7 shown to you, but each one of those basically has a joint, and even what's happening as a support is also considered a joint. So you basically have a joint at the support pin 1 and a joint at the support roller. And what happens at joints, you have members feeding in and members feeding out at those positions. So if we look at joint 8, you have a reaction feeding into that, and then you have a joint 7, 8, or a member 7, 8, and a member 6, 8 feeding into that as well. Now what's not shown on this is also what you're going to have the forces. So you're going to have external forces that are going to be applied to this. And you may only have one force, you may have several. So those are going to have to be taken into consideration once we get into this. And essentially what we're going to look at is how does that one force work its way through all of the members that are in there. Okay, so again, it's going to be an involved process. But just keep in mind, span, panel, height, those are distances, supports, which we already know. And then you have upper chords, lower chords, and web members. They essentially are all the same thing. They're just members. And those guys are going to be in either tension or compression. And then we're going to have joints. Now, let's talk about that real quick. If you think about this being a bridge, what will happen is one loading scheme that we're going to analyze is a static loading scheme. So that means if you flow through that whole truss and you figure out what member's in compression and what member's in tension and how much each member is, as vehicles would go across this, those things are constantly changing. So that gets very complex if you're looking at a dynamic loading. So we're going to look at a static loading. That's another thing that'll keep it really simple. But think about that in reality. If you're a structural engineer, you have to look at what's going on constantly. And what you'll find is that member 4, 6 might be in tension with one loading scheme, but it's going to switch to a compression after a while. So, and in fact, some of those members may be carrying no load at certain points. So we'll see how that works as we get into these truss problems. Okay. All right. So when we begin to analyze trusses, we're going to make several assumptions, and they're necessary for us to simplify the process. Okay. So we're going to look at 4 different simplifications. And the other thing I might add is, like I just said, we're going to look at this truss as being statically loaded. So those forces are not going to be changing over time while we're doing the analysis. The reality is, though, that really won't change. That really won't be static or loading. It'll always be dynamic. Okay. So there's 4 assumptions that we usually use. So the first assumption is that we consider all of the truss members connected by frictionless pins. Okay, so the pin allows it, now think about the best way to envision this is take like 2 popsicle sticks, drill holes through the 2 ends, and put a nut and a bolt together, and you could see they could just freely move. Okay, does everybody get the idea of what I'm saying?
Yeah.
What does frictionless mean then? What's the thing about frictionless? The thing with
No resistance.
yes, so what that's really saying, if you had friction besides those things being able to move freely, they wouldn't be able to move freely, but then that would also produce bending on those members. So by saying they're frictionless, we're saying there's no bending, okay? So older trusses actually were pinned, but they weren't just pinned with one pin typically. They might have had several pins, okay? Modern trusses are either bolted or welded, and they used to use rivets as well. The older trusses you'll see were old riveted structures. And if they weld them, a lot of times they'll use what's called a gusset plate that rigidly attaches those at a connection point. So this really then does have bending going on. Okay, so that's a very important concept right there. The second concept we're going to look at is that all members lie in the same plane. So for us, that's just a simplification. I'm missing the word plane in there. Just notice that. So all members lie in the same plane. And again, that's just a 2D simplification. Remember, the reality is they're actually in three dimensions. But we're never going to do anything more than that. So that's one thing we just have to look at, okay? The third thing is that all of your forces on your trusses are applied at the joints. So what we're saying is you have a joint at the one end of the member and you have a joint at the other end of the member, and we're saying that the forces are actually being applied through the joints, okay? So that gives you the fact that the bending associated with a truss is not directly attributable to the load. And it also, again, is a way for us to simplify this as we get into it. The fourth thing, well, we do have five areas here. The fourth thing that we're going to look at is that the self weight of each member is negligible. So in other words, we don't worry about it when we are doing the analysis. What we're doing is saying basically that's all been applied through the loads. So here's what you think about this: an I-beam that's 20 feet of any size is going to be really, really heavy. So what we're saying is that I-beam, or whatever type of big metal member that you're using, has no weight into it essentially, but it has been modeled into the external loads, because the external loads that we deal with are going to be so much more heavy as opposed to what the structure is itself. Okay, so we ignore that. Self-weight's ignored. And then all members are going to be considered two force members, and they're going to be either subjected to tension or compression. So this is going to be one of the harder aspects of as you guys get into this. Solving your joints, or actually you do solve joint forces, but to turn that into a member force, you might come up with a number, okay, 12 kips, but then you also further have to say, well, is that 12 kips tension or is that 12 kips compression? Because that's going to make a difference when you go to the next joint as you analyze it. So we're going to be going through an example here in a minute, and if I have time, I might go through two to get you guys going on this process, okay? So those are the five things that you look at. Again, just to recap, they're frictionless pins, all lie in the same plane. All forces on the truss are applied at the joints. The self-weight is negligible or ignored. All of the load is coming from external loading, and all your members are going to be two force members, and they're either going to be subjected to tension or compression, and that's what you have to determine. Okay. So again, for this ideal truss concept, you have two forces that exist, what are called member forces and joint forces. So member forces exist as either tension and compression due to the loading. Again, due to the loading, not the self-weight of the member. The reality is that the member would be putting some of that into the other members, but again, we're going to ignore that. And why we need this member force kind of concept, when you get into the strength of materials aspect, knowing what kind of material you have and what kind of force and what quality of force, whether it's compression or tension, is going to allow you to size that member. So do you need an I-beam that has a depth of 12 inches, or do you need an I-beam that has a depth of 15 inches? That will be determined by the forces that you're going to come up with in the members. So we'll see a little bit about, we're going to start to get into that kind of stuff when we get into the chapters later on in the book. The joint forces are reaction forces at joints created by members acting into the joints, okay? Joints will not have a compression or a tension kind of concept associated with them. So you can't say that, well, this joint is in compression, because you might have one member that's coming into it that's compression member and one that's tension member. But one thing that's really important to understand is that the joint forces at any member will have the same magnitude as the member, but they will have opposite directions for equilibrium to happen. I think I got a picture here. Okay, so here's a good picture. So notice at the top, the joint is the little dot to the left and the right of the magenta rectangle that I have there. And for this whole member to be in equilibrium, notice that there's an F1 coming out of the force to the left. There has to be an F1 force going into the right, and that's hitting that member, and that member has the same force, but notice it's going opposite directions. So equal and opposite, if you add everything together, this completely goes to zero. So that's a member force in equilibrium, and then notice the joint force in equilibrium. So, but we're only looking at one member, so you've got to understand, you could have another member coming into that joint. You could have three members coming into that joint. So we're only looking at one member. And in this case, can anybody tell me Is that member in compression or tension? Can you look at that member and tell me whether that's member is in compression or tension? Anybody?
Would it be compression?
Well, do you see the forces coming away from the member?
Oh, I do now.
Okay, so what that's saying to you is that that member is in tension. Okay? So, and we might think as we look at this, well, it says, yeah, the joint's in tension too, but remember the joint is actually compressing, pushing on that member, so the member is pushing back. But we may have another member into that joint. So we're just looking at one unique piece right here. Okay, we'll see how this works as we get into this. All right. The one thing that's really important to understand that if the joint looks like it's in tension, then the member also is in tension. A lot of people would think, well, if the joint's pushing this way and it's pushing the other way on the other side, that member's in compression. But if your joint is tensioning, the member has to be tensioned as well. Okay, so everything's equal and opposite for equilibrium to occur. That's probably one of the hardest concepts at first, but we'll see that as we get into these problems. Okay, so we use two very common methods to analyze a truss. And again, everything is going to be based on that principle of equilibrium. So that's going to make it really nice. So of course, we know that that means everything goes to zero. But one thing when we get into joints, everything is going to be a concurrent force system. So that means we're not going to be doing a moment kind of equation a lot. We will do that to solve reactions, of course, but we won't do that for other types of things, okay? So the first method is method of joints, and we're going to consider that today. The second method is method of sections, and we're going to look at that next week. So method of joints is a complex method. It analyzes each and every joint within the truss. So it can take you a while to perform. So if you have 20 trusses, or 20 joints rather, you're going to have 20 free body diagrams. And so you can see that, like I said, you could have some of these problems could take you an hour to go through. So the thing is that it's a little bit longer method. It's kind of messy, but it's very foolproof, because when you get done with this method, if everything doesn't resolve to zero at the end, in other words, sum of forces in X, sum of forces in Y, don't resolve to zero, then you've got a problem in your analyzation. So you've done something wrong. The downside is it doesn't necessarily tell you where you went wrong. So if you blew the first joint and brought that all through your truss, I mean, every joint is essentially going to be wrong. So that's the problem. The other thing that's really good about this method is that each and every member in the truss now has a value associated with it in terms of compression or tension. So you do get a complete result. When you do the method of sections, what you're going to do is selectively cross through or cut through with a section through a truss and just solve selected members. So you don't actually get the whole truss, but it's a quicker method. It's probably quicker and cleaner, but the thing is that you're only getting what you're cutting the section through. And so we'll consider that next week, but we're going to look at the method of joints today. Oh, okay, so that's going to be what we're discussing this week. Okay, so with this method, you're going to go through a process, and what you have to do is draw a free body diagram at each joint, and then you're going to use equilibrium to solve unknown forces. So each joint picture that you come up with is a concurrent force system. So we know what that means, is that all of the lines of action are coming through the same point, and the point they're coming through is the joint. Okay, so everything's coming through the joint. That means we only have two equations. So we have sum of forces in X have to be equal to zero, and sum of forces of Y have to equal zero. So if we have 5 members coming into one joint, we probably will not have enough equations to solve that joint. So we have to start at a point where we have enough solutions that we can get solved completely, and then we take that to the next joint. So one of the big things we're going to be looking at is when you start your free body diagrams, you kind of have to know where to start. And I'm going to give you some hints on that as we get into this. Okay. So here's the procedure for method of joints. You're going to solve the external support reactions first. That's very key. Every problem is going to require you to do that. Okay, that's chapter 3, and that's where we didn't do too well. So if you can't solve support reactions, you will never be able to solve a truss. Okay, so you're going to have to learn how to do this at some point, because when you get into all these problems, if you blow your reactions, you've blown the truss completely, and you will never get it to resolve to 0. Right? So we're going to have to solve support reactions first. And then Tom talks about drawing the big picture of the truss. So what he's saying is after you've find joint forces on a joint free body diagram, you're going to transfer that to the big picture. What he's talking about is you kind of have an overall picture of your truss, and you can start putting your numbers on the members and whether they're in compression or tension. Okay, so this definitely helps you keep track of joint forces. I typically don't do this till the end. And in fact, I won't be able to do that with my whiteboard that I have here, because I'm going to have to go kind of back and forth. But this is a good idea. And if you follow through examples in the book, you'll kind of see what they're doing with that. Okay, the third point is to draw a free body diagram of the starting point of the truss. So what's the starting point? That's the key. So you don't start at a joint that has too many unknowns. Okay, so you start at a joint that doesn't have too many unknowns. You need to start at probably one that has no more than maybe 2 or 3 unknowns. If you have 4 or 5, you're not going to be able to do it. So a good place, kind of a little hint, a good place to start your truss is at a support reaction. So in that case, you're either probably starting at the left side of the truss or the right side of the truss. Sometimes external loads will be good places, okay? But we'll look at that as we get into that. Once you have decided where you're going to start on that, you're going to bring in all external loads, reactions, and unknowns acting on that joint and only on that joint. So that's also, sometimes people want to bring in other forces that really don't exist on that joint. So you have to be really careful with that, okay? So you're only going to bring in on the picture the external loads, reactions, and or unknowns that are acting on the joint. Sometimes you have no external loads. A lot of times you won't have those. And sometimes you only have reactions where you have reactions that are supports. Once you figure out where you're going to start, and you've drawn your free body diagram and you've brought all the stuff into it, then you're going to apply equations of equilibrium. So you have sum of forces in X, sum of forces in Y, and that's it. That's all you have. After you solve your unknown forces, you're going to place your answers on that big picture, and then you transfer forces that are acting at one end of the member to the opposite end. So what it does is it gives you opposite directions. Sometimes that's referred to as flip-flopping. That's probably one of the hardest processes right there, but we'll look at that. Okay, so as we get through this example, you're going to go from one joint to the next joint. So let's say you solve the first joint, then you go to another joint, and you're going to repeat those steps. You draw your free body diagram, you bring your forces in, and then you apply your moments of equilibrium. And once you do that, you can then go to the next joint, and the next joint, and the next joint. So finally, you're going to go to the point where you get to every joint. So a lot of times you're going to work, let's say, from one reaction to the other. But when you get to the last joint, everything should be solved. And when it solves together, everything should go to 0, okay? So what we're going to do is we're going to look at an example. I'm going to do an example right now out of the book, and I've got another one too. And we'll see how our time goes. If you guys have a piece of paper handy, I would go ahead and get that. the first thing we're going to do is solve, we're going to solve a reaction for this truss. So this is the truss we're going to be looking at. This is out of your book, I believe. I think it's the same one that's in your book. Yeah, it is. In fact, the only difference is that Tom has that in pounds and I'm putting it in kips. So that just makes our numbers smaller, okay? So I'm going to have to clean some stuff up here, and we're going to have to do this one step at a time. So I might have to be flipping pages back and forth. So you guys need to make sure that you're keeping track of everything and keeping me on track. So this is actually the example problem on page, it starts on page 111, and that's problem 4.1. This is example 4.1. So we have a truss, we have a reaction at A and a reaction at F. Now you guys need to stop me if at any point you have questions, okay? So we have 9 feet, 9 feet, and 9 feet. So these would be referred to as your panels. So there's 3 panels at 9 feet is how we would state this truss. So the span on this guy would be from here to here, okay? So 3 times 9. So the distance of the height, let me go ahead and put that distance on there. I don't have that. That's basically here to here. And it's going to be like there. Okay. That's, let me see. I think that's 12 feet. So this is 12 feet. Whoops. It's doing that so weird now. Okay. Oh, that's why. All right. Let me clean that up a minute. Maybe I can do that. All right. Okay, so we have a 12-foot height. This is my upper chord. This is my lower chord. My lower chord is made up of members A, C, CE, and EF. So we have an 11 kip load coming down at joint E. And over on A, we have a pin. So I'm just going to go ahead and model that. I'm going to model that as up. Now again, we're just doing reactions. We haven't even gotten into the truss. This is just chapter 3 stuff. And we have a roller over here. So we're going to call this a reaction. I'm going to model this up. I'm going to model this like this. And I have another, because that's a pin over on this side, I'm going to put that pin over here. So we'll go ahead and call this reaction AH, reaction AV, and reaction FV. Is everybody okay with what I've got so far?
Yes.
Yeah.
Okay. So this is what we didn't do too well on. So let's make sure that we know what we're doing here. So this is a concurrent or non-concurrent. So what we're going to do is solve this utilizing sum of forces in X, sum of forces in Y, sum of moments, right? So I'm going to go ahead, sum of forces in X. And I hope everybody understands that right now I'm saying up to the right and clockwise, that's a positive, right? So for sum of forces in X, what do we have in X? RAH, right?
Yep.
And it's not being resisted by anything, or there's no force, right, in that direction, so that's 0. We agree?
Yeah.
Okay. Sum of forces in Y, let's see what's going on there. Sum of forces in Y, we have RAV. Now remember, I just modeled that up, so that could change. And I'm going to tell you if it does change, then when you get back into your free body diagram, you're going to want to flip it because that'll make a big difference. We have an 11 kip load going down, so that's 0. So what this tells me, RAV plus RFV is equal to 11. That's about the best I get out of it, right? Okay, so we can solve this using what?
Moment.
All right, where do we want to take it?
A.
All right, A is a good spot because that's gonna get these guys out of there and it'll solve RFV. So this is a pretty easy moment. So we've got 9 and 9 is 18. So what we have is a negative 18 times an 11 kip force, right? So 18 feet, 11 kips. It's going this way. Whoops, that's a positive, isn't it? Right? Everybody agree with that?
Yes.
And our FV is the only other thing that's in that moment equation. Remember, we're not even looking at any of this stuff yet. We will here in a minute. So 3 times 9 is 27. That gives me a negative 27 RFV. All of that's equal to 0. So if we do the math, guys, I'll take some time and do that. Again, if I'm going too fast, stop me, okay? Or at any point you have a question, stop me. So I've got RFV minus 198 divided by a minus 27. So the minus and the minus indicate that I'm going to have a positive answer. So that's good because that puts me in the right direction. I came up with basically 7.33. RFV is acting up, and that would be kips. Everybody agree with that?
Yeah.
So what does that make RAV turn out to be? We're going to plug the 7.3 into here, bring it over. It's going to come over as a negative. Gives us 3.67 positive up. Everybody good with that?
Yeah.
Okay. At this point, here's what we want to do. All right, so I'm going to go with this picture. I'm going to erase this stuff and I'm going to put in the actual numbers. Now, here's the other thing. If I had made a mistake with the direction on my reaction, I want to flip it to the right direction, okay? So when we get done with this, if this was actually going down, we want to make it go down, but it's going up, so everything's good, but I'm just going to put the number here. This is 3.67 kips. This is 7.33 kips, and this is 0 kips, but don't ignore it, okay? You're going to use it. Is that good for everybody? Everybody okay?
Yep.
Yeah.
Yep.
All right. Also, let me just say this because this is real easy to do. Do you see how easy it would be to write the 733 over here and the 367 if you weren't paying attention? Everybody see that? So pay attention to when you get done with things that you got everything in the right direction and in the right location, because that would just blow this truss too, okay? So is everybody okay with what I got so far then?
Yeah.
All right, so we have not done the truss at all. All we have done is support reactions. So this is just chapter 3. So what we're going to do now is decide what joint to go to, and we're going to start analyzing that joint. We're going to draw a free body diagram. Now I'm going to have to create multiple sketches. So what I suggest you do, if you've got paper, you can probably do 2 joints on one piece of paper. I wouldn't try to cram more than that, okay? but I'm going to have to clean my screen every time. So we're going to have to, you guys are going to have to help me when I'm going from joint to joint. Okay. I have one worked out here, but I think that I might need some help. Okay. So I'm going to say, if we're going to start at a joint, let's just kind of look at this. B has absolutely no information. Do you see that? I don't know what that joint is. I don't know what that member AB is. I don't know what CB. I don't know what BD. This would be a horrible place to start. Same thing with D. There's too many members and there's nothing coming into it or out of it. Okay. E, you could actually solve member ED, but you couldn't solve CE or EF. So that wouldn't be a good place. So typically, what you're going to find is reaction at A or the reaction at F are going to be one of the two best places. So I'm going to go ahead and start at reaction A. We're going to, and actually what I should be saying is we're doing the joint at A, okay? So I'm going to clean the screen. I'm going to wipe this out, but you've got to keep in mind what's going on here, okay? So I'm going to go ahead and blow this out, do a new one. All right, I'm going to start my joint. Okay, so I'm going to model my joint. Give me a sec here. Now, when I model my joint, okay, my joint's sitting right there, and I've got a force coming in, okay, and another member. I also have another member right here. And I have another member that's diagonally going out. Okay, so this is my free body at A. Now we're gonna put some numbers in here. So I usually like label this. I'll call that joint A. So what I know are the reactions. Okay, so I have a reaction here coming in. That reaction was up, wasn't it? We called that 3.67. Does everybody agree? We have a reaction here. This reaction was a value of what? This was 0, right? But it's still there. We can't ignore it. Is everybody with me?
Yeah.
Okay. Now, this is where you have to think a little bit. I have to decide whether these guys are in compression or tension. Okay, I don't know that. But the key here, and truly, it doesn't matter because the math is going to tell you if you're wrong. Okay, so if you called something tension and you get a negative number, it's saying no, it's compression, and vice versa. Okay, so if you look at this diagram, though, it's pretty easy to figure out. This member right here has no vertical component to it. So the only thing that can be resisting this guy is this one. And so if this one was up, this guy has to be down. So this is going to have one going this way and one going this way. Okay? If you don't see what I did there, don't worry about it. You can make them both compression, you can make them both tension. But if you look at this guy in that diagonal, this guy has to be going down because that's going up, and that can contribute nothing to that. So I'm going to call that a member AB. That's member AB is in compression because remember, joint B is up here. And if this guy is going this way, this guy has to go this way. So again, if you don't see what I just did there, don't worry about it because the math is going to tell you what's going on there, okay? But if you do this, it's just a little bit easier to make you think about what's going on, and it also gives you less negative numbers to deal with, all right? Is everybody okay with my free body diagram and how I did this? Because this is the crux of a whole joint problem. Questions? Anybody questions?
No.
All right. Do we have a concurrent force system? Max, is that concurrent?
No.
Why?
Actually, yes, it is.
Yes, it is. Every joint is going to be a concurrent force system, okay? So we only have two equations, sum of forces in X and sum of forces in Y, okay? That's all we have. If we can't solve this with those two equations, we went to the wrong joint, okay? So I'm going to write my equations. Sum of forces in X. I'm going to try to keep this small. If I can get two joints on here, maybe I can do that. That'll help us. So what's happening in the X? We have AC, right? And we have minus AB horizontal, and that has to be equal to 0. Does everybody agree with that? Remember,
Yep.
AC is horizontal, and then we have a component of AB horizontal going this way. That's the way we modeled it. Everybody agree with that?
Agreed.
No solution here, right? We still have unknowns, correct? So let's see what happens. If we don't solve this in Y, we've got a problem. So sum of forces in the Y have to equal 0. So we have 3.67 acting up and a minus AB vert acting down, correct? AC brings nothing to the table, right? Can we solve AB vert? Can we solve AB vert, Jacob?
Yeah, wouldn't it just be, I guess, negative 3.67?
Yep, but actually the negative will be on the same side, so what does that tell you?
Positive.
Yep, so what that means is we indicated the right direction, okay? See, that's not too bad. So now here's the cool thing. If you know the vert, you can solve the horizontal because this thing has a slope angle on it. It's 12 feet this way by 9 feet this way. If you go back and look at that original truss, that panel was 9 feet on 12. So you can create a real simple proportion here. Watch this. I can say that AB horizontal is to the distance over which it's acting, which is 9 feet, as 3.67 is to 12 feet, okay? So the 12 foot is to the vertical force as 9 feet is to the horizontal force. Can you solve that proportion?
Yeah, you can.
Yeah, absolutely. So let's see what we come up with. Now your book does it. He does it slightly different because he's taking like creating a. You can figure out a sine and a cosine, and this is so much simpler if you follow what I'm doing here. Okay. So much more simplistic. I come up with 275. Anybody get that answer?
Yeah, I got that.
All right, so watch this now. If we plug that 275 back into here, what does that tell us about AC? Plug that in, it's a negative, right? Comes over as a positive. It tells us that AC is a what? 275. Everybody agree with that? Nobody agrees with it? Anybody out there?
How did you set up that equation, the ABH over 9?
This guy here, Jacob?
Yeah.
Okay, let me draw this over here. Maybe this will help. This is this is probably one of the easier things to get kind of wrapped up in, but it's really not that big of a deal. So the key thing you got to remember, you're dealing with a right triangle, okay? All right, so we solved the vertical component, right?
Mm-hmm.
That vertical component has a force of 3.67, right? But the distance from here to here is 12 feet, right? And this component, A, BH, we don't know, but we do know the distance.
Okay.
So I'm just saying as this is to this, as that is to that, okay? So,
All right.
so force is to distance over which it acts as force is to distance over which it acts, all right? And that's really cool. I can use that principle, and that, in fact, that's what we're going to do because it's so simple when you do that. All right. The only thing, what that allows us to just plug that guy back right in here and solve. The only thing we now have to do to get this actual member is to just square that, add them together and take the square root. So we have to do one more step to actually solve the member. But to get the individual members, this is just a snap. Okay, you're going to see this more and more and more as we go through this. Okay, so if you're not catching it here, we'll get it. Okay, is everybody okay with that now? That's a great question. Can I erase that?
Yep.
Okay, so I'm going to go ahead and take that out. All right, so my question was, you okay with taking this 275 and plugging it in here, and then it comes over as a positive, right? Everybody's good with that? If this would have been a negative number, when you plug that in here, that would have been a positive number, and then it would come back over as a negative. So if you get negative signs floating around here, you need to handle them, okay? Is everybody good with that?
Yeah.
Okay, so here's the one thing. We have to say whether this is compression or tension for AC. What are we indicating up here, compression or tension?
Tension.
Tension. So what you want to do is come down here and you want to say T, okay? We also have to solve AB. So we're going to come down here and solve AB. AB is going to be 2.75 squared plus 3.67 squared square root. So let's see what we come up with that. 2.75 I get basically 4.6. Does that sound right? Does anybody agree with that?
Yeah, that's what I got.
Okay, units on these would be kips. You don't necessarily have to, we don't have to really worry about the units because if you start out in pounds, everything's pounds. You start out in kips, everything's kips. But we do have to say whether it's tension or compression. So what's happening here for AB? Is that tension or compression?
Compression.
It's compression. All right, this is important. All right, this is very important. An answer without the T or the C is going to be wrong, okay? All right. Okay, so we have solved the first joint. So now we have to decide where do we go from there. So since you have information for AB and AC, you either want to go to joint C or you want to go to joint B. Now, if you look at C, we're going to have a bunch of unknowns. But if we look at B, because we just solved this A member coming in, we're going to have enough to solve that, okay? You always want to go from a joint of information to a joint of no information, but you want to go to a joint that's going to be solvable, okay? And you might run into a case occasionally where that's not real evident, but we're going to go to joint B. So give me a second. I'm going to draw I'm going to draw joint B over here. Excuse me. And I'm going to do my little ruler. So I have a joint, I have a member coming into this guy. Let's see, he's coming in like this. And I have another member coming in. Like this. And I have another member coming in like this. All right. So this is member BD, this is member BC, and this is member AB, which we know. Now, this is where we're going to start with AB. What is AB, member? It's compression, right? Compression. Which way should this arrow be going in? Should it be going in like that? Or should it be going in like that? It's compression, right?
Up to the right.
Yes. So if notice, a lot of people, since this one was down, they want to do this here. That's not correct. Okay. If this is in compression, that also has to be in compression. So these are kind of, notice they're going opposite. They look like they're going opposite, but they're really not. So this is the proper way to orient this. Now, here's the other hint. I don't care about that number right there. What I want to use is the horizontal component and the vertical component, because that's going to help me solve this thing. So watch what I'm going to do here. I'm going to put a horizontal component here, and I'm going to put a vertical component here, because that's what I'm going to use to solve it. So we know the vertical component of AB was what? 367. And I'm getting that right here. And the horizontal component of AB is 2.75. Okay? So this right here, this is all critical. You're taking the information from joint A and you're bringing it over into joint B. You can see if we made a mistake in any of these numbers right here, this whole picture's wrong and everything's wrong from that point. So it collapses like a deck of cards or house of cards. It's not going to work. Okay? Is everybody okay with that?
Yeah.
Can anybody tell me which direction BC should be acting? This guy's BC. By looking at what's feeding into this, what about BC? Should it be up or should it be down? Well, notice this guy's acting up, right? For this joint to be in equilibrium, doesn't this have to be down? So these two guys have to cancel, right? And because this has just pure horizontal, vertical, this is pure vertical, and this is pure horizontal, this guy's acting right, so this guy has to act left. So my joint's really out here, and this is what I'm going to call member BD. Let's stop and talk about this and see if there's any questions. Did anybody see what I did there? Or why I did it? We solved AB. We solved it as compression. When we brought it over here, we brought it in as compression. And notice which way we're acting. Vertical with vertical, horizontal with horizontal. Another common mistake is that you put this one up here and that one down there. If you do that, obviously you've blown the problem, okay? Can we solve this joint? Mitch, can we solve this joint?
I'm following along.
Okay. Do you think we can solve it?
I'm not entirely sure.
Well, we have two equations, right? Sum of forces in X, sum of forces in moments, and we really have two unknowns. So it should be solvable. Let's see what happens, okay? Yeah, I know this is rugged, guys. We'll have a lot more time to deal with this on the board on Thursday, so it'll make a little bit difference, but we'll go through it, okay? We'll get through it. Sum of forces in the X have to equal 0. So what's happening in the X? We've got 2.75 minus member BD, no other forces in the X, right? So that has to be equal to 0 by equilibrium. So what does this tell me? That BD is 2.75. And I came up with a positive number, and I indicated this as compression. So that tells me I was correct with my assumption that it is compression. Okay? Sum of forces in Y. Have to equal 0. So in Y we have 3.67 minus BC has to equal 0. That's also solvable. So therefore, BC, you bring that guy over there, or you bring them both over. If you got negatives on both sides, it's still the same thing as being positive. That also gives me 367. It's a positive number, so that indicated that I am correct, and this is now considered a tension member. Okay? So there's one solution, there's another solution. So this one was a heck of a lot easier than this one because I didn't have to worry about anything that was diagonal feeding into it. All right? Are we okay so far? You guys following it at least? Is there any way I can make that simpler?
Not really.
Okay. So let me ask you this. So now we have joint A and joint B resolved, right? So where do you think a good joint would be to go to next? Either joint D or joint C is what I'm looking at. So I'd say we either want to go to one of those two. What do you think would be the better of the two?
C,
Right. Why would you say that?
because you already know BD and BC.
The BD isn't going to help us down at joint C. But you do know AC, right?
Yeah.
And you know BC? Those are feeding into the joint C. So you actually know two of the members coming into that, so you only have two unknowns essentially. So C would be good, yes. D, the only thing you would know at joint D would be member BD, and that would not be enough. You've got those two diagonals and one vertical on the joint D. Just too much information, unknown, right? So I'm going to erase this side. So I'm going to kind of be flipping back and forth, but I may need some information from you guys for AC, okay? So just if I ask for it, just let me know. So let me clean this up a minute. I'll leave that other side there. I think this will work pretty well. Okay, so we said that we could theoretically go to joint C. So give me a sec here. I'm going to go ahead and draw joint C up. Now, I always like to start with my joint, which I kind of didn't do in the other piece. And I'm going to draw what I know coming into it, and then we'll label everything. So I know I have a vertical member coming into this. And I'm not going to worry about which direction it's acting yet. Even actually, I know that one already, but we'll get to that. And then I got two horizontal components coming into this. So I got one here that's feeding into it, one here that's feeding into it, and then I have one like here feeding into it. So when we just look at that, it looks like a real mess. But what we've got going on here, if we look over here, we know BC, which is this member. BC was in tension, so this has to also be tension. And we know the amount of tension, that was 3.67. Okay. What did we solve? This is member AC. What did we solve AC to be? You guys need to help me on that one. What was AC? Compression or tension?
It was tension.
It was tension? Okay, so that means it's going to be acting this way, right?
Yeah.
And what was the value of that? Was that 275?
That's what I have written down.
Okay, so that's 2.75. Okay, so we have two unknowns here. And actually, it's kind of like, I like to think this has actually got two unknowns. So it's really kind of 1, 2, 3. But all right, so let's look at the diagonal. Can we say anything about the diagonal in terms of which way it's acting? Remember, this is going to have both a horizontal and a vertical component, but this guy's only going to strictly have horizontal component. So the vertical component of this guy has to counteract the vertical force, which is this guy. So which direction should this guy be acting if we think about that? Is it going to be tension or is it going to be compression? Or does it matter?
Isn't that going to be tension?
If you put it tension, you're saying this, right, Max? Right?
Yeah.
Okay, so if that's tension, isn't there a component going to be going this way? That plus that's going to mean this whole joint's going to be doing what? Flying up, right?
Oh, yeah.
You see what's happening?
Yeah.
Okay, so here's the thing though. It really doesn't matter if you model this as tension because you're going to get negative numbers, okay? So, I mean, that's not a big deal. But if you just think a minute when you do this stuff, if you think about this and think, okay, this has to be going down like that, it just keeps you from getting negative numbers, that's all, okay? But you don't have to do that. So if you don't see what I'm doing, don't worry about it, okay? Now, the thing is here, I know this is going to have a component going this way and this is going this way. So that's kind of a no-brainer. Which way is CE going to go? Left or right?
Right.
Has to go to the right. Otherwise, you're not going to have, again, you're going to have movement, right? And everything is based on equilibrium, which is really cool, okay? All right, so let's go in here and see what we can solve. So we got sum of forces in X have to equal 0. So in X, we have negative 2.75. That's coming from this guy right here. What else in X? We got plus CE, right? Plus CE, but then we'll have a negative CD horizontal. You guys agree with that? Negative 275, negative CD horizontal, positive CE. So we're not going to get a solution, but we can simplify that. I can definitely say that CE minus CDH. And I can bring that guy over. He's going to come over as a positive. So not going to give me a solution. So if I don't get a solution with y, we went to the wrong join. Okay, so I'm going to drop down here. Sum of forces in the y have to equal 0. So in the y we have 3.67. And this guy's acting down, so that would be a minus CD vert. This guy has no vertical component, so then that has to equal 0. So this is nice and solvable, right? CD vert. Bring that over, they're negatives on both sides, so that means we indicated the right direction. So Max, if we had done what you said initially, we would have a negative number there. Doesn't make a difference. It's just that when we feed it back into the equations, we just have to use the negative sign. That's all, okay? So if we know the vertical component of this CD vector or member, we can solve the horizontal component because we know the geometric relationship between those two guys. So again, I can say the horizontal component is to the distance over which it's acting, which is 9 feet, as the vertical component is to the distance over which it's acting, which is 12. So if I write that proportion, CD horizontal is to 9 as 3.67 is to 12. Now, if you had a negative here, you would put a negative up in this proportion because you got to get a negative for that guy as well, okay? So I like to try to keep my negatives to a minimum, and that's why I like to try to look at this and analyze it a little bit before I get into this. But if you don't see that, don't worry about it. It's not a big deal, okay? It's not a big deal at all. All right? So we can solve CD now. Does everybody agree with that proportion? Everybody see where I got that proportion? Just like we did before.
Yeah, I got it.
Okay, so we got 9 times 3.67 and divided by 12. You're getting 275. Are you noticing that a lot of these numbers are the same? Everybody noticing how that's kind of working out? A lot of those numbers are the same.
Yeah.
And that's gonna be true on a lot of these trusses, okay? Particularly if they have the same angles. Now, if the angles change, then you're gonna see some differences creep up, but you're gonna see a lot of the numbers keep kind of going to the same thing, okay? So that's just kind of keep your eye on that because that'll be something that you'll look at. So what does that tell us about CE? When we take this guy, we plug this back down into here, that comes over as a positive, right? So we have 2.75 plus 2.75. So that gives us 5.5 for that, that member, correct? CE becomes 5.5. We indicated CE as a tension member, so therefore this guy is tension. So the only other thing we have to do now is solve CD. I'm going to drop that over here. CD is going to be equal to 2.75 squared. That's that number plus 3.67 squared. I'm going to put CD right here. We've already solved that one before too. Again, you're going to see a lot of the same numbers creep in. That's just kind of be on the lookout because if you're not getting that, that might indicate you got a mistake somewhere. I get 4.6 again. Yeah, so we already had that number. 4.6. And we indicated that as a compression member. So that's 4.6 kips compression for CD. Okay, so we've resolved 3 joints now: joint A, joint B, and joint C. Okay, so who can venture well, first of all, let's stop. Are we okay where we are now? Does everybody understand where we are so far?
Yeah.
Okay, so now where would you want to probably go from here? Joint E, joint D. Anybody take a guess?
E.
E would be really great. E is going to resolve really quick. That's a great place. And the reality is you probably have enough information to also solve D. Okay. So you could go probably either place, but since if I look at that, I think, oh yeah, E's really simple. In fact, I can look at that and already tell you what the numbers are going to be for those guys because it's that simple. And after a while, you guys are going to get that way too. You'll be able to look at these things and just say, yeah, that's real simple based on what I've got going on. So we're going to go ahead and we're going to jump down to joint E then, okay? And again, you guys might have to help me with some numbers if I don't have them set up. And I'm going to go ahead and I'm going to describe this as joint E. And there's my joint. And we have actually 4 members feeding into this. Well, 4 things. Actually, we have only 2 members, 1 external load. Excuse me. So I have an external load. Now, whenever I do problems like this, I always put my reactions in or my external loads first, because some people will actually forget external loads, but we have an external load here. In fact, this is the only external load of 11 kips, okay? The other thing we know feeding into this is we just solved member CE, and we solved member CE as a tension member. So tension is going to take it this way, and that value is 5.5. Can anybody see how simple this is now? We only have 2 unknowns here, right? And if this guy's pulling this way, which way does the member EF have to pull? You don't want it going this way, right? So wouldn't this have to resist like that? And this will be EF. How do I model ED? Up or down? What can I model ED as? This is E, D's up here. Irvin, up or down?
Up.
Up, right, because notice you got 11 down and these guys are not doing anything, right? So the only way you're going to get equilibrium is that guy goes up, right? So we're going to call that member ED. Perfect. So look, this one's pretty simple, right? Because you got sum of forces in X have to equal 0. In X, we have a negative 5.5 plus a positive EF has to equal 0. Therefore, EF comes over as a positive 5.5. And that tells me that that is truly a tension member, okay? So I said, you can almost look at that and figure that out by inspection without even doing this. I would not do that though. I always write this out, okay? Even as long as I've done this stuff, I always write that out. That's critical. And then we're gonna say sum of forces in Y. And I'll tell you the reason that's critical is because if you come through these problems and you've made a mistake, what that will allow you to do ultimately is if you've got everything written out, you can go back through and kind of figure out where your mistake was, potentially. Not always, but sometimes. So for the Y, we have a negative 11 plus ED has to equal 0. Okay, so negative 11 plus ED. Remember, these guys are nothing in the Y. So therefore, ED is going to be equal to 11. And we indicated tension, so that's definitely a tension member. All right? That one wasn't too bad, was it? There's your answers. Are we good on that?
Yeah.
So we have 2 more joints to do. We have joint D and we have joint F. So it doesn't matter, but you have to do every joint, okay? Because the last joint is going to tell you, you know, whether everything goes to 0. So anybody have a suggestion on where we go next? I can assure you we have enough information to solve either one. So it really doesn't matter. Do you guys want to go to D and then maybe we'll end at F, the reaction? How's that sound?
That's fine.
Okay.
Yeah.
All right, so I'm going to go ahead. Now, I might need some help from you guys again on this one, okay? Because my pictures, I keep blowing my pictures out. So just if I need it, let me know, okay? Give me that information. Let's see if I can get those out of there. Delete. Okay, so we're going to go to D. That's what we said, D, right?
Yeah.
Okay. I almost forgot what I said. All right, the D looks really messy. So we got to take our time. All right, so let me, there's my joint. All right, now I have a member feeding in this way, which we actually know that was BD. And then we have a member feeding in this way, which we just solved. We also have a member feeding into this. Which is this diagonal. And that would be the diagonal CD. We know that one. So the only one that's got unknowns here is this guy coming that way. So it looks rather messy, but it's really not. I'm going to start with ED because I know ED. So ED is a tension member, so that means we modeled that as tension like this. So that would be 11 in tension, okay? Let's see, CD. Can anybody tell me what we came up with for CD? Was that tension or compression?
It was compression and it was 4.6.
Okay, so it was compression. Now, the 4.6 I don't care as much about. I really want the components, okay? Because they're a lot more useful. So what I'm going to do is draw my components here. I have a horizontal component for that guy and a vertical component for that guy, okay? They're way better when you start doing these kind of things to think about. So if that guy's going that way, this guy has to be going up and that has to go right. Now, let's make sure we get the right numbers. What was the horizontal component for that one, for CD? Horizontal component was this guy. Was that 275?
Yeah, it was 2.6.
Okay. 275. And then the other one was what, 367? Is that right?
Yeah.
So remember, I don't really care about the magnitude, but these two guys are all important, okay? Because they're going to help me resolve it. So then we had another member, BD. And what did we determine BD to be? That was, we did that like second joint. Was that a compression member also?
Yeah.
Okay, so if that's a compression, then he's also coming in like this. And I think, was that 275 as well?
Yeah.
275, okay. So now we need to determine which way this is going. And this is pretty easy if you look at it. If this guy and that guy adds together, this guy has to counteract it by going that way, right? So doesn't that tell me this guy has to be compression? The other thing that's important too is if we notice that minus that, I'm going to have more pulling down on this. So this guy also has to be, one has to be going up and one has to be going like that. If that's not true, then something's wrong. Okay? You guys see that? Again, if you choose to make this tension, it's not a big deal. You're just going to get negative numbers, but you're just going to have to deal with the negative numbers. All right? So at the end of the day, that's not an important thing. But the more you can do that up front, I feel that that's easier. So I'm gonna model DF as a compression member, and I'm gonna put that guy right here, DF. Okay. So let's see what we get here. Sum of forces in X have to equal 0. So in X we have 2.75 from this member, which was BD, and we have 2.75 from the horizontal component of that member, which was CD. And then this one's going to be minus DF horizontal, and all of that's equal to 0. That's solved, doesn't it? That gives me DFH is going to give me what? 5.5? Those two added together come over as a negative. Negatives on both sides tell me that that's a positive number. Does everybody agree with that? Everybody see what I did there?
Yeah.
So you can see where this free body diagram is all important. I couldn't do any of that without a proper free body diagram. Okay. All right, so let's see what's going on in the y direction. Sum of forces in the y. So we have 3.67 up, minus 11 plus DFV has to equal 0. So we have 11 minus 3.67 gives me a negative 733. When it comes over, it's going to come over as a positive 733. Okay. So we have both the vertical and the horizontal components. Okay, so let me say something here. If this one is positive and this one is negative, you've got a problem. Okay, if they're both, if one's positive, they both have to be positive. If one's negative, they both have to be negative. So we're good right now. I'm going to show you another little trick you can use to check yourself. since we know the vertical component and the horizontal component and the vertical distance and the horizontal distance, we can write a proportion that should agree. So I can say that the 5.5 horizontal force is to 9 feet horizontally as 7.33 over 12. If that doesn't agree with itself, then we got a problem. So I'm going to take 5.5 and divide it by 9. And I get 0.6111. And I'm going to take 7.33 and divide it by 12. And I basically get the same number. Little bit of rounding going on. So these agree. So that pretty much tells me I'm good right to this point. Okay. You don't have to do this here, but this is a nice little check. Does everybody see what I did?
Yeah.
And also, again, remember what I said. If this is negative, this has to be negative, and vice versa. If one's positive, they both have to be positive. So if you come up with a negative up here and a positive down here, that indicates to you that you've got a mistake somewhere. It's impossible, okay? Because that would say your vector is like going this way, okay? The wrong direction into that joint, and that's impossible, okay? So we need to now solve df itself. So that's very simply done by Pythagorean theorem. So that's going to be 7.33 squared plus 5.5 squared. And so df will be equal to, let's see, 7.33 squared plus 5.5 squared. I came up with basically 9.2, and I can round these. So I'm going to call that 9.2. That would be kips, but more importantly, it's compression. Okay. So we have done now joint A, joint B, joint C, joint D, and joint E. So in this process, you have solved every member, but you still need to do one more joint because you've solved every member, but you don't know if you're correct or not. So when we go to the last joint, if everything doesn't go to 0, we've got a problem. Now I can tell you almost directly that because this relationship worked here, that we know we're probably good, but we don't know that until we actually write the equations and look at the free body diagram, okay? So I'm going to go to joint F now. I'm going to clean this guy up over here on this side, and we'll resolve it at joint F and see what comes up here, okay? And hopefully we're good. And if you're not, then we got some issues somewhere, and we just don't know where that is, but we'll figure it out. Okay, so let's see. Close that. So the last joint I need to go to now is joint F. This is my joint right there. I have no vertical components on this. I do. I take that back. I do have a vertical. I have a reaction on here. I have that roller reaction, okay, that we started with. There's a roller reaction. That's a reaction. And I have, let's see, I have that diagonal member coming into this. Which is doing this. Okay. So at this point, we know everything. We just have to complete that. So we just solved this guy as a compression member. So this is going to be compression like that. And with compression, and since it's a diagonal, I'm going to have two components on that guy. So remember, the components are the things I want to model, not anything else. So use those components. Okay, so this guy's going this way, and this guy's going this way. And so the horizontal component was 5.5. And the vertical component was what? 7.33. You guys would have to look, what was this member right here? That was member EF. I can tell you this, looking at that, that better be tension.
Did you say EF?
I did.
Yeah, it was tension, it was 5.5.
It better be, right?
Yeah.
Because if that's going this way, this better be going this way, right? And it better be 5.5, which it was, right? Is that what you said?
Yeah.
Perfect. What was reaction, the RVF reaction that we solved initially? That was 733 up. This is the reaction, right? Can you guys see what's happening here? That plus that's going to go to 0. That plus that's going to go to 0. If that doesn't in one or both directions, you blew your truss. But let's go ahead and we're going to write it out. Sum of forces in X equals 0. We have negative 5.5 plus a positive 5.5. And that equals 0. That checks. We have sum of forces in the Y. We have 7.33 minus 7.33, and that also checks. So we have completed this problem, and when we get to this point, everything went to 0, resolved to 0. We have a completely done truss. All of the members are correct values, and we also know their quality, whether they're compression or tension.
Well, it's nice that you can check it off with the
It
last
is.
part.
But here's the part that's not so nice, Max. Let's say you had 20 joints and
Yeah.
you get to the end here and that doesn't check. So what does that tell you? You
Pretty
got a
much
problem,
screwed.
right?
Yeah.
And you don't know where it is. Now, sometimes, okay, here's what can happen sometimes is that you'll get the horizontal to go to 0, but you won't get the vertical. So that probably tells you somewhere in a vertical calculation you went awry. You know, that's the best it tells you, but you know you can't get much better than that. So it's just, yes, sometimes just have to go back and debug it. All right. Now let me give you a hint. Okay, if you do come up with problems here, okay, the first step, the first place I would check is your reactions, because I'm going to tell you, most students, 90% of the time they're doing reactions wrong, okay? So that's going to be a big issue. Always, if you get a truss that doesn't resolve, look at your reactions, because that's probably a good place to start. If the reactions check out okay, then that means, okay, you blew one of the free body diagrams somewhere. So the only thing you can do is just kind of go back through and look at each picture. That's really why I recommend you write everything out and you do really good pictures, because if you do have to like debug something, you can pretty much go back through it and find where the mistake was and then work it from that point forward, okay? But this is not an easy process. It's going to take you a little bit of time. And you have to think about that compression and that tension concept. And that's, again, not a big deal, but, you know, you just got to think about it. Also, and I didn't probably emphasize this, but I should, when you have an external reaction or you have an external force, you notice when we're doing these things, they flip-flop direction, right? The numbers flip-flop direction. External loads and external support reactions never flip-flop. So they're always going to be in the direction they started in. They're never going to move, okay? Also, another pitfall that people get into is they forget an external reaction at a joint. So for instance, if I had back here at D, if we had a reaction or a joint force, let's say an external reaction coming in here, and we forgot it on this, that would make a big mistake too. So really take time when you're drawing these pictures up, take time to really look at what's going on here, okay? Because I've said this before, that 50% of your problem is right here, okay? If you once you set up that free body diagram, that just kind of leads you down the path of what you're going to do here. And all you've got on joints is just sum of forces in X, sum of forces in Y. That's it, okay? Now you do have proportion. Proportion can help you when you got diagonals, but that's it, okay? So you're really limited, but you're never taking any moments at a joint because a joint is a concurrent force system. All right, let me see if there's any question. I don't think we're gonna probably have time to do another one, but I've certainly, yeah, I've got another example, but it's a pretty big one. I could probably do that. I could probably do that with you guys on the board or something, but we're going to have plenty of these to work on. So does anybody have any questions they'd like to, or anything they want me to go back through on this?
No.
It's just a process. You got to do it, okay? That's really the only thing I can say. You just have to do it. Let's take a look at some problems in the book real quick. We're not gonna work them, but I'll just give you some hints on these, okay? And now let me see. I want to go to my Blackboard side a minute. Let's see if we can go here. So you should have. Let's see. So I opened up this page for you, or that folder. Okay, so there's your trust terminology PDF. That's kind of a nice one that's separate out of that. The homework problems we want to do for Thursday, and you probably won't get them all done, but for Thursday, the 1, 2, 3, 4, 5, 6, 7, and 9. So we're skipping 8. Let's go ahead and we'll look at those real quick. Some of those, I'll give you some hints on some of those. I would probably start with problem 1 because it's actually a really nice, simple, easy truss, okay? So you might want to start with that one. And it's got a lot of nice symmetry going on in it. So you'll probably find that the members are going to be the similar left and right, okay? So 1 is a really easy one to do. Keep in mind that you have a pin on the left and a roller on the right. So a pin at A and a roller at C. And again, I can't emphasize this enough. You got to get the reactions right. If you don't get the reactions right, you're going to have issues, okay? Let's look at problem 2. Whoops. Switch me out. Problem 2. Problem 2 is a little bit more involved, okay? But it's actually a pretty good one. And you can actually start at joint E for problem 2 and then work into like A. So if you try to start at A on that problem, you're going to have too many unknowns, okay? So I would probably start when you get problem 2, solve your reactions first. You got your pin at A, a roller at C, but then probably start at joint E and then go down to A, and everything will roll pretty well. But you don't want to start at well, you could probably start at C as well. And the reality is too, you can go from 2 different directions. So I could start at E and then come to C. So I don't have to go in an order. It's just kind of nice to work in an orderly fashion. Problem 3 is going to take you a while, okay? So problem 3 is there's an involved truss. So if you're going to do that one, take your time with that. Problem 4 is pretty straightforward. The only thing a lot of people do is they get the roller reaction going the wrong direction. That roller reaction should be going down. Okay, so just think about that one. Problem 5 is real challenging. You might want to wait. I can do that one on the board on Thursday, so you might want to just hold off on that one. 3 and 5. 6 is pretty easily. 7's not a bad one. That's a good one. Okay, and 9 is a pretty good one. All right, so I would say if you have time to do any trusses between now and Thursday, do problem 1, do problem 2, and do problem 4. I think if you do those 3, you'll get your feet on the ground with them pretty well. And then we'll work some of the harder ones. But I will, we'll have 3 hours on Thursday, so we can solve a lot of trusses while we're there. Okay. Does anybody have any questions?
No.
Anything they want to discuss, before we get out of this? Because, like I said, I don't have enough time to actually get you into another trust by the time we go through it. I just don't think we'll get it done. I will have I do have office hours tomorrow, so I'll be in my office from 8 until 1. So if you would have a question, just go ahead and send me a question, whatever. All right. And I do have some YouTube videos. I'm gonna post these later, but I do have problem 1, 2, 4, and 9 worked out. I'm not gonna put those out there until we go through this stuff on Thursday. Okay. Any questions then?
Nope.
All right. Well, I'm gonna stop the recording here, and what I'm gonna do then? Let's see. Let's see. That didn't work. Stop the recording. I'll stop the recording now.